We are here again with integration by substitution, and in this slide we are going to be discussing extensively about the direct method of integration by substitution. In our early classes we might have studied that this method is applicable. We can write this method is applicable to integrate expressions by introducing a new variable to consume parts of the equation or expressions. So I hope students are getting this. What I'm trying to say here is that whenever you are talking about integration by part, students should always keep it in mind that you are actually dealing with a situation whereby you are going to bring in a new variable to make sure you actually cancel out parts or that we consume part of the variable. As already discussed, you can take some examples to actually understand what we are talking about. We can take the first one to understand the process. So we are in the first explanation to the integration method. I've given you some direct formula, but one thing that makes students not to understand integration is because integration don't have some particular ways and formula you can apply directly like differentiation. So I take the first one, I'll take it one by one. First one says we have the integrand of tan x dx. As we have already studied that tan x does not have a direct formula like differentiation. So in this case, we are going to apply our trigonometry knowledge to solve this type of question. And about trigonometry knowledge, we might have been told that tan x, right, as a sine x over cos x. So what we do here is now direct substitution into this. So we turn our integrand with tan x, which is our sine x, divided by cos x, then you have your dx. So now, the thing we now do is like, we now introduce a new variable. Now, that's in such a way, because many times my students will ask me in classroom that, sir, how did you actually know the variable that you are going to bring in, as in which one will it represent, numerator or denominator? The logic is this. If I introduce variable t, just like our chain rule we have discussed in our differentiation, we can say here, I will say let t equals to cos x. Now, student will say, why is it that I am going by cos x and not sin x? Because I know if I differentiate back cos x, I'm going to find what the numerator, which is sin x. So this is the methodology we use to actually get the answer. Because I know after differentiating this, dear student, I am going to get back the expression on top. And if I get back the expression on top, it's very easy for me to cancel then and integrate. So we are now, after introducing the variable, as you can see, we are now going to put in the differential part of the variable. We differentiate t with respect to s, we know, and say dt equals to, whenever we differentiate cos x, everybody knows we are going to get sine x, then you have your dx. What have I done here for those who are just joining us? What I've done here is, like I said, dt dx. I hope you understand. That is finding the derivative of t with respect to x from our trigonometric value of differentiation. Cos x is going to give you minus sine x. I have only done what we call multiplication here to get this second expression. So I hope students are following this. So please, if you have any doubt, just keep in comment section. I will attend to them. So here, if you carefully look at this now, we are now going to substitute this so that this can be consumed. So now it's now easy for me to bring back the expressions I have here into the question. So if I bring back this, you can do it directly. See here, t is equals to, you can see t is equals to cos x, as you can see here. So if I see sine x over t one by one, then sine x here, I've already made something here. Look at, if you make sine x over a formula, this is sine x dx. It's not sine, we have sine x dx. Excuse me, there should be x here. X should be here. So that is sine x dx. So now here I can make, you can do it basic way. Let me just make it very simple. So you can say therefore, this is too long, but I just want you to see it. Here you have ds. You can make ds for a formula. You now say dx is equals to, this is too basic, but we can just follow that. So if I make ds of the formula, it will be 1 all over, we have negative 1 over sine x dt. I hope you understand this. You can say sine s equals to, or sorry, ds equals to dt over minus sine, which is same as minus 1 over sine x dt. Why I'm doing this is because it's the first example. As I move forward on this, you'll get it very well. So you now come back to what you're integrating. I don't want to waste our time. Remember, it was integrand of sine x divided by cos s you have taken to be t. Where is that? This is it. So over t. So remember, times now dx that was here. Dx now you have taken to be negative 1. You can see negative 1. I'm only showing steps, all over sine x multiplied by dt. So this is just too long for us to be following. Then you can cancel out this and this. So what you have now, say therefore, I don't want to rush us. The integral, we can bring out negative 1 as a constant, or bring negative here. From negative outside, what do we have left? 1 all over t dt, which is very simple to integrate. So directly for next examples, I may not be actually showing all these steps. You can see I've actually bring in this t to be equals to negative sine s. What I just need to do here is that negative sine s ds, then I multiply to give me 1 over cos s is t directly. You can see this is minus sign. So minus sign will consume minus sign. I will know it will cancel out. What I have here is minus 1 all over t, which is directly. So here, what I do next is just to integrate negative 1 by t. So we have that. We have already given us our direct formula that 1 over any expression is just nothing but ln of it. So here we have negative is outside. 1 over t is a natural log of t, then plus the what? Arbitrary constant. Remember, t was equals to cos s. Final answer will be equals to negative ln of t, which was cos x, plus c. So this is the way we do integration by substitution, and I don't want us to have any issues with this. And that is the first one. We can quickly take another example. We have a lot of examples to do in this slide. Looking at example 2, let's take our integration of ln of x as natural log of x divided by x dx. Just like what I have said, now you can see I will look for what can consume this. And by bringing a variable, I love using phi. So t is equals to, from here, now ln of x. So I take t with respect to x, dt by dx. So dt equals to ln x, or ln of x, natural log of x, is equals to, from differentiation, is 1 over x dx. So what I'll do here, I'll just directly substitute that back here. Then I'm going to have, I told you, you can go through all this long process, but you don't need it. What I'm going to have here, this will cancel out this. What I will have is a t, then I have t dt. So integrating t dt, everybody knows this is an algebra form. Give me t raised to the power 2 over 2 plus arbitrary constant. Recall that t equals to ln of x. So I have ln of x all square, or you write it as 1 over 2, best way. Ln of x, now you have all square plus c will be the question answer. So I hope students are getting this, because these are the basics, and the basics are always very, very important. What I did here, I told you, if you are not so good in all this, make the s of the formula, follow my steps. And when you make the s of the formula, substitute back in the s here. Remember that ln of s is t. You can write t over x times, and what you have here is dt over that. then you see it's going to cancel out. So you can always follow the first method to break it down, but you can do it directly because we are moving forward into direct substitution. So the next one I'll take, you can take another example here for proper understanding of this concept. About the third example, we can look into this. Let's take, we have this. We have to integrate. I'm taking more of the trigonometric expression, sec squared of x all over tan of x. As you all can see, dx. Now, if I differentiate tan x, I am going to have sec squared. So the variable I want to be, which is always t, I love t, will be equals to what we consume over here. So I have t will be equals to tan x. So dt dx, everybody knows dt will now be equals to sec squared x dx, which we consume. Consuming means we cancel out. So from there, I can now say, therefore, what I will have left in my integrand now is now, after it has consumed, it will be, dt is now sec squared x dx, so it will be 1. And I have taken tan x to be t, it will remain 1 over t. Follow my steps from the first example, which show details on how to get that. It's very simple. This will take in this, it will cancel out, because this will cancel out this. I just do it directly. But follow my example here. Just make the S over formula. Substitute back, you will see it will remain this. So if I integrate 1 by t, everybody knows it will give me what we call ln of t plus c. Recall that t was equals to tan x. Final answer will be ln of tan x plus the arbitrary constant. I hope students are getting this. So please always have it in mind that substitution method is employed in such a way that it will always consume the first part. We can take 2 more. So let's see in this slide, we can take 2 more before we move to the next slide. Here we take another example. Let's say we have something like this or of this nature. Let's take algebra form so that it won't be only that. We have integrand over 2x plus 3 all over x squared plus 3x plus 1 dx. We have to integrate that, and basically we can say if we take t to be this, because this we consume when you differentiate, is the 2t plus 3. So this is the method. It's kind of very simple now. So we can say t value is equals to, what is under is x squared plus 3x plus 5. Because it will consume the numerator, I say I differentiate the t will now be equals to 2x plus 3. Then you have what? Dx. So here is substitute back. So therefore, what we are integrating here, as you can see, it will consume each other. Then you have 1 by t2 yet again. So you can finish this. So you can finish this very simple, or you make the S of formula. The S will be equals to dt. As dt, you can see what I'm doing here. Dt all over 2x plus 3, we cancel it. There's nothing but 1 over t. Just like what we have. So the same answer. You can finish, it will give you ln of, that is t, which is now x squared plus 3x